Hello everybody, welcome to your second lesson of the week. Our objective for today is that we're going to be learning about some new terms. We're going to learn about Avogadro's number. You're going to be able to explain the term the mole in regards to chemistry, and we're going to continue practicing converting numbers to scientific notation, much like we did in our last atom unit. So our agenda for today, we're going to kind of look at the year. Then we're going to talk about scientific notation, and then we'll get to our final subject of Avogadro's number. So, we're kind of coming to an end here, guys. I know it's sad because we're not all here together, but I wanted to give you a chance to look at all the amazing things that you've learned this year. So first semester, you were brand new to high school, and you learned about physics. All of these different properties, you became masters of them. Second semester, we've moved on to chemistry. These are the units we've worked through this semester. We just finished the bonding unit online, and we're in our final unit of the semester, Unit 5, classifying reactions in the mole. So take a second, pat yourself on the back, because that's a lot of scientific information that you have learned and absorbed in this year. Don't forget how awesome you are. Now, we're going to talk a little bit about scientific notation, kind of review that. We talked about it when we went over the unit on the atom. Hopefully you remember we watched this video in class where they zoomed out from a man's hand sitting on a picnic blanket in New York City. They zoomed out to trillions of miles away from our galaxy, and then they zoomed in all the way to the point of the atom. And what this talks about and tells us about is how we use scientific notation, powers of 10, to help us express really large numbers and really small numbers in a way that's more manageable and easier to write and calculate. So for today, these are the materials that you need to take out. You're going to have the scientific notation Avogadro's number note taker that we're going to go through in this video. And then the backside is a scientific notation activity, which you're going to be working on in class today. So let's talk a little bit about distances and different units of measures that we use. We talked about measurements. It was our very first unit that we did in this entire class, and we've grown and learned so many different types of them. So if you're dealing with smaller objects, whatever measurement you're using should accurately match what you are measuring. So a really small object, like for example the width of a pencil, you'd want to measure with something really small, like a millimeter. If you have a slightly larger object, let's say the width of your textbook, you're trying to measure the binding on that, millimeters is going to be a little bit too small. You're going to bump your measurement up to something a little bit bigger that matches the measurement you're making. So you're going to be using something like a centimeter. As we go out even bigger, and we're talking about distances far across the earth, something that we can't just measure with one ruler, if you're looking at football fields or how tall a building is, you're going to want to use the meter. And remember, we're always working in scientific notation, but if you have to kind of convert that so it makes sense in your head, a meter is about 3.28 feet. So if you want to say how tall your house is, you're going to measure that in meters. We then bump up to kilometers, which is 0.6 of a mile, to measure shorter spaces on Earth and distance. So we're kind of talking about, like, if you're talking about the circumference of the Earth, how far is it all the way around our planet? Well, that would be 40,000 kilometers. Little extra numbers there, but you know, that's not too crazy of a number to interpret when you're talking about kilometers. It would be much different if we were measuring the distance around the Earth in something small like millimeters. Then we go beyond our Earth, distances into space. So if we're just talking inside of our solar system, our 8 planets and the sun, we're going to use a new term called an astronomical unit, which we write using AU for short, because that's a really long word to write out. This is a really big distance. 1 AU is equivalent to 93 million miles. Whew, that's amazing. So we want to use something like this to express distances, for example, like from Earth to the moon. Going from the Earth to the moon is 238,900 miles. That's a really big number. So instead of describing something in miles or meters, we can use a unit like an AU, which expresses a large distance in a smaller number. We can also use these to go outside of our solar system. So going even bigger, we're going to talk about the light year. Now, you've probably heard this before. I know our friend Buzz Lightyear likes to talk about this a lot.
To infinity and beyond!
And 1 light year is even bigger than an AU. It's over 63,000 AUs. So something like this helps us figure out a distance, let's say, from where we are now to our closest star. So our closest star is Alpha Centauri, which is, in scientific notation terms, 2.52 times 10 to the 13th miles away from here. That's a really large number to comprehend. We could also talk about it in terms of light years, and Alpha Centauri is 4.3 light years away. Then we can get even bigger than that, and we could talk about a parsec, which is equivalent to 3.26 light years. So these are different distances in astronomical units if you're trying to see what kind of these distances are, to kind of wrap your head around them. So if you wanted to go from Earth to Venus, it'd be 0.3 AUs. If we're going to Jupiter, 4.2. Neptune, even further away, 29.6 AUs. And then our former 9th planet, 47 AUs away. A little bit more about a light year. Where does that term come from? Well, it's the distance it takes for light to travel in 1 year. So when we talk about waves in the electromagnetic spectrum, what we learn is that light acts like a wave and it travels at a constant speed, and it doesn't have to be inhibited by anything. And it can travel for a really long time in distance, especially in space. So I don't know if you guys have ever heard someone say, someday when the sun explodes, we're not going to know if our star exploded for 8 minutes. I wonder if you've ever heard anyone say that. People used to say that to me when I was a kid, and it was kind of hard to understand. Well, what does that mean? Well, the sun is really far away, and it takes a certain amount of light years for the light from the sun to travel to here on Earth. Now, sun's actually close compared to other stars in our galaxy, but it takes 8 minutes and 20 seconds for the light from the sun to travel here from Earth. Now, that's smaller than 1 light year. So the sun is smaller than 1 light year away. But what that tells us is that it takes a fraction of a light year, 8 minutes and 20 seconds, for that light to travel. And it's a lot easier to think in terms of time like that than it is to talk about how far the sun is away in terms of meters. So go ahead with that information, pause and take a moment on this note taker to match the units of measurements that you have here at the top to the different kind of examples here you have in this list. Okay, so let's go through this. So the width of a pen, you would measure in a millimeter. The width of a book in a centimeter. Height of a building would be in meters. You'd measure the distance around the Earth in kilometers. The distance from the Earth to the sun, this is some of the new things that we just learned, you would use an astronomical unit. If you're looking from the distance to the nearest star, and we're talking like nearest star like Alpha Centauri outside of our solar system, you're going to use the light year. Distance to the nearest galaxy, even further away, hard to even comprehend, you're going to use a parsec. Now, one that I did not go over is something that's really small, something that we talked about a lot in our unit on the atom. How would you describe a distance that's the width of an atom? You're going to use something called an angstrom. So it's really, really small. It's equal to 1/100th millionth of a centimeter. So in scientific notation, 10 to the negative 10 meters. So you're moving your decimal place over to the left 10 times to equate exactly how small that is. And then how many bagels are in a dozen? 12. So, a little bit of a reminder on scientific notation and powers of 10. We use powers of 10, so you heard me just say this term, times 10 to the power of blank, and we use that to describe numbers that are either really, really big or really, really small, depending on the notation. So, for example, if we were to measure the speed of light in meters per second, here's this number that we have. 300 million meters per second. But that's a lot of zeros to write all the time. So we can write this as, if we move the decimal place over from where it is after the last zero, how many times over do we have to move it to the left? 1, 2, 3, 4, 5, 6, 7, 8, until the decimal point is right behind the 3. Which gives us a scientific notation of 3.0 times 10 to the 8 meters per second. We're able to describe that number in scientific notation so we don't have to write as many zeros. What if we're talking about a really, really small number? Something with this many zeros, which is the mass of a dust particle, incredibly small amount of kilograms. It's going to be really tedious to have to write all those zeros. So let's count how many times we have to move the decimal point over to the right in order to get the decimal point right behind the 7. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since we moved the decimal place over to the right, we're going to say that we moved it to the power of negative 10, indicating that this is a really small number. So if we want to express this mass of a dust particle in scientific notation, we write 7.58 times 10 to the negative 10 kilograms. So just a little bit kind of an overview. If you're going from a number and you're moving your decimal place to the left, that means you're going to end up with a scientific notation that is positive, that tells you it's a big number. If you're going from a number to scientific notation and you're moving your decimal place to the right, you're going to end up with a negative scientific notation to indicate you're dealing with a really small number. Okay, so that ends scientific notation, and we're going to talk a little bit about a new term, which we're going to continue talking about over the next week and a half, which is a new unit on a mole and Avogadro's number. Okay, when I say mole, there's a couple things you might think about. And it's not this, even though it's scary but also cute, it's not that kind of mole. It's a mole that we use in chemistry. And what it is that it's a unit of any substance that contains the Avogadro's number of atoms and molecules. So it's a unit of measurement that we can use in chemistry to measure something really, really small like an atom. But within that definition, there's a new term, Avogadro's number. Well, what is that exactly? Well, it was measured by a man, Mr. Avogadro, and what it tells us is the number of atoms or molecule in a mole of any substance. And that number is equal to 6.02 times 10 to the 23rd. Whoa, in scientific notation, that number is huge. You'll kind of also see that these definitions are synonymous with each other. You can't have a mole without acknowledging Avogadro's number, and you can't have Avogadro's number without acknowledging the mole. They're kind of one and the same. And what we use moles for is we use it as a unit of measurement to create an equal playing field to measure how many atoms or molecules we can have when we're looking at a compound. So for example, how many cats do you need in order to have 1 mole of cats? Xander really wants to know the answer to this, and the answer is 6.02 times 10 to the 23rd cats. A mole is it's an equivalent of Avogadro's number of how many of that substance you are looking at. We use this to determine in chemistry something called molar mass, which we're going to talk about in future lessons.
Mole is an animal that burrows in the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now say you had a mole of pennies to distribute round the world. Give to each of the 5 billion grown-ups, boys and girls. There wouldn't be a single soul down and out of luck, 'cause everybody in the world would get $1 trillion. Or say you had a mole of paper and stacked it toward the sky. Paper's awful thin, but that pile would get so high it'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times. And a mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a mole of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and, of course, block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating 1 marshmallow each second. Not 2, 'cause that'd be cheating. With 5 billion people munching, how long you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. But say you had a mole of atoms. Would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You could hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
So a mole is just a unit. It's not a mole on your face. It's not a mole that digs in the ground. Just like a dozen, a baker's dozen, a mile, years, parsec, a light year, a mole is just another unit that we use to measure things, but in this terms, it's really helpful to measure things that are really small. So we're going to conclude today's lesson by practicing some of our scientific notation. You're going to complete this entire page, but I'm going to go through a few of these examples with you. So the first one, it says, time to practice. Write each of the following in the correct scientific notation. So number 1, you're going to want to count. So you have a really big number, and you're going to want to count how many places do I move my decimal point to the left so it's right behind the 3. So I'm going to count 1, 2, 3, 4, 5, 6. Which gives me 3.2 times 10 to the 6. We don't have a unit here, so we don't have to write it. Number 2 also gives us a really big number. You have 13,500. From where the decimal point is now, how many places do I have to move it to the left? I'm going to go 1, 2, 3, 4 places to the left, which gives me 1.35 times 10 to the 4. Let's also jump and look at number 5. We have 0 point, and then how many zeros do we have? Let's count. 1, 2, 3, 4, 5, 6, 7 zeros. And we want to move the decimal point over one more time so it's behind the 4. So we're going to move the decimal point 8 places. And since we're moving the decimal point to the right, we get a negative scientific notation. So we get 4.0 times 10 to the negative 8. So you're going to practice the rest of those in that section. But I also want to give you an example. How do you go from scientific notation to a number? So looking at number 9, you have 5.6 times 10 to the 4. Since it's 10 times to the 4, it's going to be a big number since it's positive. So we're going to move the decimal place over to the right to make our number bigger. How many places are we going to move it over? Well, we're going to move it over 4 times. So if we go 1, 2, 3, 4, we get 56,000. Let's also try number 13. This is going the opposite direction. We have 7.9 times 10 to the negative 5. That negative tells me that this is a really small number. So I'm going to want to move my decimal place over to the left in order to make my number smaller. So if I have to move it over 5 times, I go 1, 2, 3, 4, 5, and I get this decimal place, 0.000079. Okay, so you're going to finish the rest in that section, and then the last portion says to solve the following problems. So you're going to have to use a calculator for this. Sometimes something new in your calculator is that not every calculator has a times 10 button. Calculators use a function called EE. And this lets you multiply by a power of 10. So I'm going to show you how to do this using a common everyday calculator. So let's start with this first problem. We have 3.4 times 10 to the 3 multiplied by 5.67 times 10 to the 9. So let's start with our first number to put into our calculator. So I'm going to go 3.4, and now I have to see how do I put in this times 10 to the power of. We're going to use a button on your calculator called this EE button, and it's above the x to the negative 1 exclamation, or to the exponent. That EE signifies a power of 10. The way you get it to show up on your calculator is, since it's blue, you have to hit second EE, and the E will show up, and the next number you have to put afterwards is to what power of 10 do you want to put it to? Well, you want to put it to the power of 3. So that's our first number. I'm going to multiply that times 5.67. Now I want to do my power of 10. Second EE, so to the power of 9. Once I have that inputted in my calculator correctly, I press equal, and I get my right answer, which is 1.927 times 10 to the 13. Okay, so let's say you don't have a calculator at home. Well, lucky for you, all you have to do is go into Google and type online scientific calculator, and Google has its own calculator that you can use. So I'm going to do another example of number 21. So that one says we're going to do 4.9, and this time to get my powers of 10 button on Google, I use EXP, and you'll see my E pops up. And this one has a negative power, so it's a small number, so I'm going to use times 10 to the negative 3. And this time I'm dividing, I'm not multiplying. I see that by that slash, so I'm going to go divided by 1.33 times 10 to the power of negative 7. Check that it looks like what I have written on my piece of paper. I go ahead and hit equal, and Google gives me an answer that's not necessarily in scientific notation. It says 36,842. What you're going to want to do is convert that to scientific notation. You move your decimal place over, go 1, 2, 3, 4 places, and you get 3.6 times 10 to the 4 for your scientific notation answer. So today's assignment, you're going to finish the rest of the scientific notation worksheet that I did not already go through. And this is, you're going to submit this as a Schoology assignment by Friday. And it's going to be 15 points added into that test grade. So the more and more assignments you do for this, the better your test grade category is going to be. And also, this is our last lesson for the week, so make sure that this is everything that you've completed this week. Last lesson, you should have worked on your outline. Today, you're working on your scientific notation. That's 25 points for the outline, 15 points for the scientific notation. Both of them due by Friday as a Schoology assignment. Of course, don't forget, if you have any problems submitting something to Schoology, you can always email me your assignment. I'd be happy to accept it that way as well. Thanks so much, guys. Let me know if you have any questions. I'll be on Google Hangouts or email if you need me, and have a great rest of your day.